Okay, we are in energetics of locomotion. And again, our focus is on running. And this video is part 3. All right, now I want to continue to emphasize this link between different areas of kinesiology or exercise science. And I know you've heard terms like aerobic work or aerobic power or anaerobic work and anaerobic power. Those are all terms that are very useful and used pretty commonly within exercise physiology. And obviously, these are terms that we've gone over in our mechanics. These would be your physiology. Well, what these terms are telling us is that information of how we're taking our food and we're converting it, or fuel, maybe a better way to do it, because we have some fuel in the body, and converting it or transforming it to, in essence, mechanical energy. Okay, remember, we have the heat that comes off of here. And sometimes we do this using oxygen. Sometimes we do it without using oxygen. And when we use oxygen, we are talking about aerobic work and aerobic power. And power representing how fast we're transforming that energy from one form to another, from the fuel, from the chemical state to the mechanical state. The work is telling us how much we're converting over, how much we're using oxygen. So that would be more the energetic cost of locomotion, part 2, or was that part 2? Maybe it was part 1. It was part 1 of this series of lectures. Total amount of oxygen used, how fast we're using oxygen aerobically, or in the anaerobic sense, we're not using oxygen at that sense. We have other metabolic processes that can still accomplish work and can still do work in a particular time period. This all happens faster, and that's why if you are into sports like power lifting or sports like high jumping or even sprinting, you want to understand these metabolic pathways to really understand how you generate mechanical energy from fuels that are available in the body. You still generate heat. And again, that goes back to direct versus indirect kilometry. You still generate heat when you do these metabolic pathways here. They just happen faster than the aerobic processes. These can just happen over a longer period of time. Okay. And that's why a lot of times when we're talking endurance performance, we're really focused in on this. But we still need to know these processes, because a lot of times in a race, you have undulating terrain, maybe a quick hill you need to get up, or a long hill you need to get up. Or maybe you have some race strategy that's happening, a breakaway, or you've got to change your pace quickly in response to what someone else is doing, a competitor. So we still need to know this anaerobic metabolic pathway, but a lot of our focus ends up being on the aerobic. It has to start here, and then we add in this information as we go along. But the same concept is applying. We have chemical potential energy in the body, and we transform that chemical energy to mechanical energy through some metabolic pathways. And so that's the link between our physiology and our mechanics. Let me give you a little bit more sense of some of our mechanics and what we may do in something like running. And I'll give you a Reader's Digest version. Yeah, I don't know if you know what Reader's Digest is, but a Reader's Digest was always a condensed version of longer stories. And I'll give you the short version here. Interesting enough, a lot of times the mechanical work that we look at, it's not always easy to match up with the physiology piece. So there's also often some real neat discrepancies that we need to try to tease out and understand. I'm going to present one way to do this, and I'm going to give a sort of a big picture perspective of of, of, of generating information about power from the mechanical perspective. And I'll do it from the sense of position, velocity, and acceleration. I've done some of this already in other lectures, and I'll do this for the center mass of running. And on the x-axis is time, and my marker is running out of ink here, which means it's almost time for a break. And on the y-axis of the first plot is position, and below that is velocity. And I'm not going to go through generating this because I've done this in other videos. And if you want to go back and practice this process and understand this process, it's good to do. But I'm going to just do it quickly, just for the sake of illustrating something. I'm going to put force, I'm going to put GRF here, and this is time down here. And I'll deal with just the vertical force right now, okay? So I'm going to just deal with the vertical force component. All right, so our position plot, we hit the ground, our center mass goes down, back up, off into the next stride, and this is coming in from the previous stride. Our velocity, we strike the ground. This is ground contact. This is toe off. We strike the ground with some negative velocity. We speed up just a little bit in the beginning, and we slow down, and we speed up, and we take off, and then we're a projectile at that point, and we're projectile prior to ground contact. And our acceleration, this is ground contact, this is toe off. We start with some negative acceleration, and we get a peak. Oh, that's too long, sorry. Oh, I'm messing up my plot. It was so beautiful in a second ago. We're going to do this, and then we're going back down, and then I'll go off -9.8 before I did. I need to do an eraser with my markers, okay? And our ground reaction force starts ground contact. And I've noticed for those of you familiar with ground reaction forces, know that there's some other things that happen in this region immediately where the foot is contacting the ground. I'm still drawing that it's too little, the slope of them. Okay. We sometimes will have that impact peak, and then it will come back down and do something like that. Sometimes you get some other neat details in there. I'm just sketching out a general form of it. Okay, so here's our typical PVA model for running. Well, now let's just think quickly in terms of power. Set of notes. This is number 2. I gotta keep them straight myself. This is number 3. Remember, power is rate of work done, so work over time, or it's force times velocity, because this is FD over T. Okay? So force times velocity. So one way to get at power is to actually take our force profile and multiply it by our velocity profile. So we multiply our force profile by our velocity profile. I'm going to do that right here, but I'm going to do it conceptually. I'm not going to draw out the pattern, because the pattern isn't as important right now as understanding the concept. We get a little more room here. So I'm going to try to show you've got. I'll do the same plot here. Sorry, I don't have enough room. I'm going to put power here. And notice I've left, and this is units of watts, regions where power can be positive or negative. Because if we look up here, we're going to have regions where velocity is either negative or positive. I really did a sloppy job here with my sketch. The acceleration and force per alpha should match up nicely. Yeah, when you get to student comments on the course evals, you can say, oh, his sketches are a little messy. All right, so let me try to unmess them a little bit. It's I get a little focused on details sometimes, but here we've got some negative velocities and we've got some positive velocities, okay? Positive velocities up here, all right? And in this case, we're going to multiply those velocities times the ground reaction force. And the ground reaction force is always positive. It does not go negative. This is an upward directed force pushing on the runner. So if I come back down here, I'll draw this right here. And so if I take a positive number times a negative number, I'm going to get negative power. And if I take a positive times a positive, I'm going to get a positive power. So now I've got regions where power is negative and we've got regions where power is positive. Okay. Well, conceptually, what we interpret this to mean is the force and the velocity vectors are in opposite directions whenever power is negative. In this case, our force is positive, and that means our velocity is negative. And when power is positive, that means both force and velocity are acting in the same direction. So remember, power represents transforming energy from one form to another. All right. In this case, what we typically talk about with negative powers is we are changing the direction of the velocity or the velocity and the force are in opposite directions. So something is happening to velocity, not only in magnitude, but also in the direction. And so we talk about energy being absorbed where we have negative power. And when we see positive power, force and velocity are acting in the same direction. And that means that we're generating energy. So we're going from, we're moving downwards, but we're applying a force upwards to slow the person down and ultimately to stop the person from moving downwards. Here, this is the second part of stance. And again, we're thinking vertically. Now the center of mass is moving upwards, velocity is positive, and we're speeding velocity upward. So we're generating power to propel ourselves off into the next stride, into the next flight phase. All right, so that's a very simple way of looking at it from running. We do this a lot in the angular world as well, where we look at joint moments and joint velocities. And when we look at joint moments and joint velocities, we will plot out the joint moment on one axis, or excuse me, one plot, and the velocity plot on the other. And the third plot would be power about that joint. And the same thing, the same concept exists. When the joint moment and the joint velocity are in the same direction, we're generating power or we're doing a concentric contraction. When joint power is negative, that means the joint moment and joint angular velocity are in opposite directions. So that would indicate an eccentric contraction, most likely, depending on how the task is laid out. So this is just a simple way of looking at the relationship between mechanics and power, in that we're looking at how our force and velocity profiles are matching up in order to understand power. And that power still represents the how fast we're transforming energy from one state to another. In this case, we're transforming energy in a way that we're trying to reduce the kinetic energy during the first part of stance. We're trying to reduce the downward velocity. In this part, we're actually trying to increase the kinetic energy. We're trying to increase velocity of the center mass prior to takeoff. So in this case, our transformation of energy starts to be almost from one form of mechanical to another form of mechanical. But ultimately, that will be related back to the chemical energy to mechanical energy as well. Because remember, power is transformation from any form of energy to another form of energy. So in this case, we're reducing chemical energy, and what we would be increasing would be something like elastic energy. Maybe we're storing this energy in the form of stretching the tendons. And then those tendons end up gaining potential spring energy due to the stretching of the tendons. That was just a concept. All right, so we're transforming the kinetic energy to something else, to some other form of energy. During walking, sometimes that's a little easier to look at in terms of there's this interplay of potential energy and chemical energy that's really easy to see in walking, and with potential energy being the height of the center mass, and that is increasing and decreasing, while kinetic energy is doing almost the opposite of what kind of potential energy is. So there's this interplay between those two forms of energy. It's a little different with running simply because we've got this flight phase that's happening here. And so it's a little trickier to look at. But in essence, the same concept is happening. We're reducing kinetic energy. We're increasing kinetic energy. We're absorbing energy is what we would say anecdotally or word on the street, and we're generating over here. Power is negative because force and velocity are in opposite directions. Positive is power. Is positive because force and velocity have the same direction. Okay, so that's just an example of taking energetics of locomotion and not just thinking VO2, but thinking more about mechanical power. Okay, thanks.